Hello everyone, welcome to another exciting installment of Dave Does Math at Home. Today we're going to talk about section 2.1, Basics of Functions. We're going to talk about section 2.6, Function Combinations. And then we're going to talk about section 3.2. We're going to get into graphing polynomials. Not all on this video. My camera does a weird thing where it will automatically truncate. Oh, hello, Harvey. My camera only records videos in like 15-minute chunks. So, those sections will be a couple videos. And here's Harvey. She's making noise. Harvey, look at the camera. Yes, good. Say hello. Okay, she's not being talkative now. She only talks when I put her on the ground. So, let's get right into it. Section 2.1, Function Basics. The first and most important question we need to tackle in this section is, what is a function? This, as a question, is given a lot of very brilliant mathematicians a lot of grief for a lot of centuries. People have been struggling with this question. The current official, mathematically correct definition of function is honestly kind of a hot mess. It's not very useful. It's not something that I want to get into right now. So, the working definition that we're going to use for our class, that is going to be really useful for us and actually meaningful, is that functions have three important characteristics. First of all, they are equations. Y, the output variable, is some function of x. You need to have this equals sign. Without an equals sign, you don't have a relationship, and the function needs to express a relationship between x and y. So that's the first piece. It has to be an equation. Second piece is, it's got to have two variables. X and y. Y is the output. X is the input. You choose numbers for x, you plug them into the function, you get numbers for y as outputs. So for now we're going to treat these functions as if they're like input-output machines. Eventually we're going to start we're going to start thinking of functions as objects instead of, when you think about it as like an input-output machine, you're thinking about a function as a process. It is a series of actions that happen to one number to produce a new number. And that's useful to a point. One of the biggest goals of pre-calculus is, ultimately we want to start thinking about functions not as these processes. We don't want to think about them in terms of a list of instructions for what happens to a number. Ideally, we want to start thinking about functions as objects, not processes at all, just objects. Like, this is its own entire function, like it's its own self-contained like unit as a thing. It has a graph, that graph has a shape, and then you can do other new exciting processes on this function, like adding 1 to it to see what happens, or taking a derivative when we get to calculus. Before we can do any of those actions on these functions, we need to start thinking about functions as objects themselves. And we'll get there hopefully by the end of the semester, but for now, at the very start of the semester, we're this input-output function machine process model. This is going to work really well for us. The third and last piece you need in order for something to be a function is each input must have exactly one output. This is important for reasons of ambiguity. As an example, we can look at something like x squared plus y squared equals 25. This is the equation for a circle of radius 5 centered at the origin. And at first glance, it kind of looks like it's a function. It's an equation. We've got that equal sign. That's what we need. We got two variables, x and y. It's also what we need. This third condition is going to give us trouble, though. If we pick a number, even a super simple one, if we pick x equals 0 and look at what y has to be, we end up with y squared equals 25. And this is going to give us two potential outputs. Maybe y is 5, maybe y is negative 5. This kind of ambiguity is what we want to avoid with this rule. In order for us to be able to talk about these things meaningfully and know exactly what we're talking about all the time, it's important that we don't have any of this confusion. We need these relationships to be such that if you choose a number for an input, you're always guaranteed going to get exactly one number for an output, no ambiguity, no possibilities, just one thing, it's definitely that thing, no confusion. So this circle is not a function. Graphically, this third condition is usually referred to as something called the vertical line test. We graph this circle of radius 5 at the origin. 1, 2, 3, 4, 5. This is your circle of radius 5 centered at the origin. This x equals 0 point is this vertical line right here. So if you put that vertical line here, it'll cross your function, it'll cross the shape twice. If you put a vertical line on a shape and it hits it twice, then it fails the vertical line test and it's not a function. You need to be able to put vertical lines anywhere you want, and they should only cross your shape once. Or cross the shape. I guess the official way to say that is they should only intersect the curve once. So if we have a different function, let me grab an eraser. If we make up a different function like y equals x cubed minus 2x, something like this, this function probably looks like this. And the nice thing about this function is you can put vertical lines anywhere you want on this axis, and anywhere you put a vertical line, it's only going to intersect the curve at one point. These vertical lines are x values. Those are our inputs. They correspond to exactly one output. That is them hitting this graph in one position. So that's the vertical line test. Okay. That's the basics of functions. We're going to get this erased so we can talk about evaluating functions. Let's take a function like f of x equals x squared plus x minus 2. If you're being asked to evaluate a function at, say, 7, it just means you look at what this function is doing, and you plug in 7. What this function is doing is it's squaring something, it's adding that thing to itself, and then it is subtracting 2. So we'll put 7 in there and there, and simplify. We get 49 plus 7 minus 2 is probably 54. Okay. That's all there is to evaluating functions. The interesting thing about this is that even if you plug in weird stuff like Q, it works exactly the same. F still does this same thing, squares a thing, adds a thing, subtracts 2. So you just put Q in here. Now you have a function of Q. If you're doing this to something weird like K minus 1, it still works exactly the same. F is going to square something, it's going to add the thing and subtract 2. Except here we're going to put K minus 1, K minus 1. Now there's a lot more simplification that has to happen. K minus 1 squared is K squared minus 2K plus 1. If you're following along at home and you didn't remember this minus 2K, don't do that. Exponents do not distribute over addition and subtraction. You have to FOIL this. Plus K minus 1 minus 2. This should give us K squared, once we start combining like terms, minus 3K. Oh no, this is a plus K, so it's minus 1K. Minus, so K squared minus K, 1 minus 1 minus 2. This is what happens when we plug K minus 1 into F. And that's function evaluation. That's pretty much all there is to it. This technique, I think, is pretty important. It's worth emphasizing again. It's really handy to think about F in terms of empty parentheses instead of x's. Because one of the big things we're going to do in this section is we're going to be replacing x's with things like 7 or q or k minus 1. And when you see these functions, you kind of want to have x's in them. Like it's kind of, we have a lot of practice thinking about these in terms of the presence of x's. So taking the x's out and writing this as a bunch of empty parentheses that you can replace with whatever you like 7s or q's or k minus 1s or whatever else you have, I think that this is a really good way to think about function evaluation. That's basically all of section 2.1. I'm going to cut this video here, and we'll do a 2.6 video real soon.